Now we are ready to put our knowledge of rational functions to use by finding out how the graphs of rational functions work. And one of the most common things known about rational functions is that their graphs typically have asymptotes. And so today we are all about finding asymptotes. You already know a couple graph of rational functions because there are a couple of the graphs that we do as our basic shapes back earlier in the year. We all know our good friend y equals 1 of x. Hopefully someone out there is going, oh, that's a hallway. And we know in this case it has the x and y axis are asymptotes, and it goes curving into the opposite corners. That's a simple rational function, but rational functions tend to make graphs of that type that have horizontal and vertical asymptotes. In fact, here in a few minutes, we're going to discover you can even have slant asymptotes. So the key thing is asymptotes typically only occur with rational functions. The only other functions that have asymptotes are our very specialized ones, such as exponential functions, logarithms, hyperbolas. But some of the trig functions have asymptotes. So typically, though, the only ones where we see with just a straight algebraic function involving x to powers, here's going to be with rational functions. In other words, you have to have a fraction. If you don't have fractions, you're not likely to be seeing asymptotes. So our question, though, is going to be, how do we tell where asymptotes occur at? Well, we have to analyze the types of things that can have asymptotes. And we can have them in several different ways here. We can have asymptotes which, if you give me a second, oh, that one is dotted. Okay, never mind. Hang on a second. I'm trying to change colors here. I can have a graph that has one or two vertical asymptotes, perhaps a horizontal asymptote. Graphs like that tend to have kind of somewhat traditional curves. Just like our butt cracks and hallways tended to fit in the corners, you'll often see ones like this. In one of these corners on the outer edges, you might have essentially our hallway curves, but going up the middle, you might have a parabola or a scrabola. Now, it is legal to cross a horizontal asymptote. Horizontal asymptotes are there to show what happens as you extend outward to negative and positive infinity at the left and the right. Going through the middle, you can cross an asymptote. It's okay. That's a very traditional type. We're actually about to discover here that you can have what are called slant asymptotes as well. And slant asymptotes, typically problems with slant asymptotes will also have a vertical. So you might have a vertical, and a slant is literally a diagonal line. Now, these types of functions tend to do one of two things. They either go following the outsides of the asymptotes, going up the slant and then up the side, coming up the vertical, going up the slant. That's one typical method you will see them. You will also see them with, if I draw you a different version here, I'll put the vertical on this side this time and then throw a slant up through there. Sometimes they tend to fit inside between the two, in which case you might get a function that comes down and then curves and goes back out, and it can come up in here and then curve, so it may say in between the two asymptotes, but typically does one of those two things. Finally, you're going to be excited to see this one. You can also have functions, let me get another coordinate system going here, that have what we call nonlinear, my calc book calls them curvilinear asymptotes. You can have asymptotes that are truly parabolas or scrabolas, that type of thing. So I can have an asymptote here that is a parabola. It might also, in fact very likely, might also have a vertical asymptote as well that might say be coming down through here. Didn't do so hot with my dotted lines there. Let's try that again. And so if it does something like that, what kind of a curve might fit into those? Once again, it tends to either follow the outside edges. It'll come along this one and then branch and go down the vertical on one side, and then may come up here and then follow out along that one. Sometimes, though, it could stay on the inside of these as well. So you never know what way it's going to follow until you plot a few points. But it tends to follow one asymptote for a while and then switch over to the other one. All of these are created with rational functions. So our question is going to be, how do we locate where the asymptotes are at? That's what we're all about. So let's go play. Okay, up here in the top right, I have an equation we all know and love. We know that that's 1 over x again. That's our hallway. You all can tell me that it has shifted where. And brief pause a moment. I need to get this permanently set so I don't have to keep changing it every time I want it. Okay, so now we know that that's going to have a horizontal asymptote. That baby is going to be shifted up 3. Oh, missed completely on that one. Try again here. That's a little better. It's going to have an up 3, right 2 shift. Okay, so we know we have asymptotes there. We know it's a hallway. That it's going to follow the upward curve and follow this one, do something like that. I'm not going to worry about plotting exact points at the moment. Okay, you can tell where those asymptotes are at on this one. But when I give you a rational function, it's not going to be written that way. A rational function is going to be written all with a common denominator in one big fraction. So I'm actually going to convert this to a common denominator form by making a common denominator of x minus 2 here. And if I do that, I'm going to have x minus 2 on the bottom. That's going to make 3x minus 6. So when I add it together, I have 3x minus 5 over x minus 2. Don't worry, you aren't going to have to do this. This is the form they are going to give you to start with. They're going to give you a function like that and say, okay, tell me where's the horizontal and the vertical. Okay, we already know, we just figured out, we already know that this one has a vertical at 2 and a horizontal at 3. The question is, how do you look at it in this form to find it? Okay, well, what's telling me the vertical's at 2? Well, what do you see on the bottom? You have x minus 2. Where does that equal 0? 2. So vertical asymptotes are quite easy to find. You find verticals by determining where the denominator equals 0. Verticals aren't a problem. Okay. Horizontals, on the other hand, are a touch trickier. We know this one has a horizontal at 3. The question is, what's really telling me how to get that? Well, you see that there's a 3 on the 1x term, but why would I pick just that individual 3x term and go, oh, it's 3? It's got, at least if I'm picking the x term, I need to take both x terms. And that's exactly what you do. If you take the highest power of x that you see in the problem, in this case x the first, and you take that term from top and bottom, 3x over x, and you simplify it, you're left with 3. So therefore, there is a horizontal asymptote, and we will write horizontal, there are horizontal lines, we'll write them as y equals 3. We know that that is going to have a horizontal at 3. So when you want to find a horizontal asymptote, you're going to find the highest power of x in the problem, determine the highest power x, and then you must take that power from both the numerator and the denominator. So we're going to practice with that here shortly. But that's how you're going to find horizontal verticals, and at the moment we're sticking just with that. I'm not going any fancier than that. So let's do a few practice problems here and see if we can just identify horizontals and verticals. Now, there's no law that says you have to have a horizontal and a vertical in every problem. That is not the case. You can have, some problems will have just a horizontal, some will have just a vertical. Okay, we're going to start relatively nice here. And we're going to start with y equals 3x squared plus 1 over 2x squared minus 8. I want you to find, right now, strictly the horizontal and vertical asymptotes. Okay, we just said verticals occur where the denominator equals 0. So if you want to find the verticals, you've got to go, well, where does the denominator equal 0? Which you can either factor it or solve it. A lot of times you'll have to factor it. This one would solve really easy. I'm going to go ahead and factor it since typically you do have to factor it. If I pulled a 2 out, I get x squared minus 4. If I factor it, I would get plus 2 and minus 2, which means I have two answers, 2 and negative 2. Okay, but you do have to remember vertical asymptotes must be written as vertical lines. All vertical lines are written in the form x equals. So your actual final answer would have to be x equals negative 2 and x equals positive 2 for your vertical asymptotes. Okay, horizontals, on the other hand, are a different story. When I want to do horizontals, then the steps say find the highest power of x in the problem. What is the highest power of x you see in this problem? It's x squared. It says take that power from the numerator and the denominator. So you would take the 3x squared, and on the bottom is 2x squared. And when you cancel that, you're left with 3 halves. So therefore, your horizontal asymptote would be at 3 halves. Now, how do you write the equation of a horizontal line? You write it as y equals 3 halves, so your answer must be written y equals 3 halves. There would be your horizontal and vertical asymptotes. It's crucial that you write them in the correct form. Okay, but there's probably some questions in your mind and you're going, but what if? Because there would be some special situations where this just doesn't always work the way I'm showing you here. So let me show you a couple others of what happens, what if the same power isn't in the numerator and the denominator. Okay, so let me give you y equals 4x minus 1 and 2x squared plus 5. And I want to find, once again, horizontals and verticals. Okay, verticals are where what happens? Yes, where the denominator equals 0. Okay, that's not going to factor, so I'm just going to solve it. If I, actually, let me save a little space here. That's going to subtract and become negative 5 halves. What do I do then? I square root both sides, and I get the square root of a negative number. That means it's imaginary. What's that mean? I can't have an imaginary vertical asymptote, so therefore there aren't any. There is no, should have written that in white so we can tell that's the final answer, that there are no vertical asymptotes on this one. There's no law that says there has to be. So the verticals are none. When I want the horizontals, I am going to take and look for the highest power of x. What's the highest power of x you see in this problem? It's x squared. And notice I said you have to take that power from the top and the bottom. But you're going, there isn't that power. There's no x squared on top. Therefore, when you take it from the top, you take it as 0x squared over 2x squared. What's going to happen? The x squareds cancel. 0 divided by 2 is 0. So therefore, that's how we get a horizontal asymptote smack down the x-axis at the line y equals 0. So there would be a horizontal at y equals 0, but no vertical in this particular problem. Okay, I'm going to attempt to squeeze one more on here because I have the next screen all set up. There's one last burning question in your mind, I'm sure. And that is, okay, what if I reverse that last one on you? What if I switch it and I actually have the larger power on top and the smaller power on the bottom? Okay, once again, I want the horizontals and the verticals. If you try to find the vertical, what's going to happen once again when I set it equal to 0 and solve it? I'm going to get again a negative number in a square root. So still no verticals here. Beware, anytime you have something squared plus a number, that's going to give you an imaginary. It's not going to work. Okay, horizontals. I'm taking the highest power of x. In this problem, I see the highest power is x cubed. So I'm going to take 3x cubed from the top. I don't have an x cubed in the denominator, so I'm putting a 0x cubed. And I'm left with 3 over 0. That's undefined. So what's that mean about my horizontal? Yes, indeed. It's also none. This one has neither a horizontal nor a vertical. However, it does have one other kind, which we'll get to here momentarily. But it's possible. Maybe you don't have any asymptotes. In this case, there's no horizontals or verticals. But you're going, what else could there be? The burning question appears. So I mentioned earlier at the beginning that there can be what we call slant asymptotes, which are basically diagonal line asymptotes, or nonlinear. This book calls them nonlinear. I'm used to calling them curvilinear in my calc book, but they can be curved asymptotes. You can have a parabola asymptote, a Scrabble asymptote, believe it or not. It's not very common, but it can be done. These occur at the situation we just saw. They occur when the numerator, actually I should say, well, okay, we can write it this way. Actually, I've got it written right here. Duh, sorry. When the numerator is 1 power higher or more. So the numerator has the higher power. If that's the case, there will never be a horizontal. There will be a slant or a nonlinear / curvilinear asymptote. So if the numerator has the higher power, you can always have a vertical. Verticals can happen with anything. But if the numerator is higher, there will be no horizontal asymptote, but there could be or will be a slant or curvilinear asymptote. Okay, just to give you a feel for what that means, I actually though want to emphasize that a moment. So what can I do here and make this pretty exciting? I didn't want that one either. Once again, let's snowflake that. That's kind of a key thing. The numerator has the higher power. There will not be a horizontal, but there will be a slant or a curvilinear. Now, what do those look like? It's pretty much what you would expect. If it's 1 power higher, it's going to be a slant. You're going to have the asymptote that's diagonal. You're going to have an asymptote that's vertical, more than likely. You don't have to, but you're going to have a slanted asymptote. If it's 2 powers higher, what shape is a graph that is 2 powers higher? What is the shape of anything with an x squared in it? It might be x squared. It could turn out to be something like x squared minus 2x plus 3. But we know that anything that has a power of 2 or higher always gives us a parabola. So that means you could have an asymptote. That's a parabola. If it's 3 or more powers or higher, it's pretty unpredictable, and quite frankly, I've hardly ever seen one of those. They're not very typical. It could be just plain x cubed, but it could also be x cubed plus x squared plus 2x plus 1. It could be a multi-termed expression with x cubed as the highest power, in which case, if it's plain x cubed, you might have a asymptote that is indeed just a plain old scrabbler. If it's this situation where you have multiple terms, it could be that's a polynomial then. And so you could have an asymptote that's actually doing some type of a polynomial curve. That gets to be a little bit challenging. So now we want to actually see if we can find these. And the big question is, how do you find it? How do I determine the equation of this slant or curvilinear asymptote? Well, you're going to be excited. It's something you just did in the last chapter. You find it by doing our good friend long division. You actually divide the numerator by the denominator, and the resulting answer gives you the asymptote. So long division is going to be the key to these problems. Now, I just ran myself out of space, so I'm going to have to add an extra page here a moment. And we're going to go see if we can actually find all the asymptotes here. And the fun, exciting equation we are going to do is 4x squared minus 8 over 2x minus 4. I want you to find me all the possible asymptotes. Okay, there can always be verticals, so let's do that first. What makes the denominator equal 0? Well, this is a pretty simple solve. If I do that, I'm going to have a simple x equals 2. And so, yes, I have a vertical asymptote at 2. Horizontals. And actually, you need to ask yourself, is it horizontal or is it going to be a slant or curvilinear? Okay, if the numerator has the higher power, there is no horizontal, guaranteed. So this is a none. The numerator is higher. You don't even need to check for it. It's going to be none. If the numerator has the higher power, no horizontal. Okay, so consequently, that means we can have a slant in this particular problem. So if I want to find the slant in this particular problem, or the curvilinear, I need to do long division. Okay, since we can see that it's only one power higher, it's going to be a slant, x to the first power. It's going to be a line. If it's 2 powers higher, it's going to be a parabola. If it's 3 powers higher, it's going to be a scrabola or a cubic polynomial of some type. So the number of powers higher will tell you what you're going to get. We just need the exact equation for it. And what did I just say you do to find it? Yes, you do long division. So we're going to do long division here. I'm dividing by 2x minus 4. Now, if you remember with division, what do we have to look out for as we write it down? Do I have every power of x up here? And no, I don't, so I'm leaving the 0x in here. Minus 8, that's really crucial. You look out for those missing terms. And the good news is you don't have to do the division out clear to the end. Once you get down to the point where you're going to have a remainder, we don't care about the remainder. We just need the original part you get from the long division. So we're keying here off of our 2x. And we're going, how would I take times 2x to get 4x squared? Well, I got to take it 2x. I'm going to multiply that out front, which is going to give me 4x squared minus 8x. And then, of course, everybody's going to remember the key to long division is change your signs. So minus plus, that's going to cancel. When I add those together, what do I have? I have an 8x minus 8. Okay. I now want to take my 2x out front here. What I have to take times 2x to get 8x? I have to take a positive 4. So this is going to make this plus 4 up here on top. Okay, here's where you actually get to stop. Once you've got that top down to the constant number, you're done. Everything else that happens here is going to be remainder stuff. We don't care. So consequently then, I can tell that my slant asymptote is simply what I have up there on top. It is the y equals 2x plus 4. That's my slanted asymptote. So here I have a slant at y equals 2x plus 4, and I have a vertical at x equals 2. Now, some of the lovely problems today, I only picked 3, ask you to actually try to create the graph of these. Most of them, you're just going to identify the asymptotes and quit. By the way, follow the instructions written on the assignment sheet. Don't follow the instructions with the problem in the book. Do only what I asked you to do. You don't have to do the extra stuff they asked you. So if they're going to ask you to actually create the graph of these, you're going to have to go through a few steps, a few extra steps, although it's not major. And I am going to ask you to do a very, very rough sketch of these. You may use graph paper, but sometimes these are almost easier without graph paper. And in this case, right now, I think I'm going to do this one without graph paper to show you that. But when you want to actually graph them, there's just, you need to find the asymptotes, of course, which we've already done. And then just like with the last chapter graphing polynomials, you need to find the x and y intercepts. And then if that's not enough to allow you to get a rough sketch of the graph, plot some additional points as needed to tell exactly where the curve is going. Once again, we are shooting for a very rough sketch of this. We are not going for a perfectly accurate, beautiful picture. So if I actually want to try to plot this, I don't know, maybe I do want graph paper here. Let me try that a second, see if I can just add a single square on here without killing the whole page. Wow, that killed a lot. Okay, that's not so good. Let me see if I can slide this down. Yeah, without extending the page. Well, all right. Nope, it's not going to let me. It's going to keep popping up. Okay, fine, we'll extend the page. Now it should let me come down. Whoa, dude, where'd my problem go? Now we're down in the boondocks. All right, we'll keep trying here. Eventually I'll get this right. Okay, that's maybe as close as we're going to get here. So if we want to plot that, you need to put your asymptotes on first. You have a slant asymptote at y equals 2x plus 4. So the big question is, how do you plot the line 2x plus 4? It's simply, yes, we have a y-intercept at positive 4 and a slope of 2. So we're going to rise 2, run 1. Now the problem we have with this is the fact that sometimes the points you have to plot are going to run this thing off the graph paper. So I actually haven't put this one on all that accurately, so we'll see. Oh, wow, that was really, really, really bad. Guess I didn't notice. I didn't get the line. Okay, we'll try again here. That should work somewhat accurately if I do a little fix on it and drag it over here. Okay, we got an asymptote. We got a slant asymptote. I also needed a vertical at x equals 2. So let's run that down in there as well. If I can find origin 1, 2. Okay, so it's one of this type. And once you've graphed a few of these, you'll know it's either going to stay on the outsides of the asymptotes, or it's going to stay caught in those V's between the asymptotes. Okay, which is why they tell you that you need to then also find the x and y intercepts so that you have some idea where the points are at. So I need to get the actual equation back down here again. 4x squared minus 8 over 2x minus 4. And so if I'm going to do x and y intercepts, if you recall, this was back with lines. X-intercepts occur where the y-coordinate equals 0. So if I'm setting this equal to 0 and I'm solving for x, okay, I'm going to have to multiply the denominator over to the other side. What's going to happen when I take it times 0? It's going to be gone. So I really just have 0 equals 4x squared minus 8. If you want an irrational function or a fraction to equal 0, you just need to set the numerator equal to 0. The denominator is going to be gone every time. So I just need to solve the top here, which is going to give me 8 equals 4x squared. X squared equals 2. So x equals plus or minus square root of 2, which, since we need to plot it, that's about 1.4-ish roughly is about the value of square root of 2. So I would know that this one has points at plus or minus 1.4, it hits the x-axis, so somewhere over in this range, 1.4 over here, somewhere over in this range. So I know it hits the x-axis there. That tells me, is it going to be in between the two asymptotes, or is it going to stay on the outside of them? And obviously this one's going to be in between the two asymptotes. So I've got my x-intercepts at plus or minus 1.4. When you want y-intercepts, we know that you put 0 in for the x-coordinate. So if I put 0 in for the x-coordinate, I'm going to have -8 over -4, or +2. So the y-intercept here is exactly a +2. Well, that's pretty much giving me an idea of what's happening on that part of this graph. I'm clearly going to follow my asymptotes. Well, I'm trying to follow my asymptotes here. Come up, hit that point, and it's going to come back down and follow out the other asymptote. So that part of the curve is very clear, but the problem is none of this information helped me get the other part. But you are assured that if this one stayed within the 2 pointed areas, probably the other one is going to be up here in this little triangular area on top. So you just need to pick another coordinate to plot on the right side of the vertical asymptote. Get on the other side of that vertical asymptote. So if the asymptote's at 2, I don't want to plot really big numbers, so I would plot like 3 or 4. I'm probably going to do 3 here. If I put 3 in this function, 9 times 4 is 36 minus 8, that's 28. On the bottom, 6 minus 4 is 2. And again, here's where I hit my problem. I'm supposed to be 14 high. So if I'm only 3 units over, I'm 14 high. There are 12 boxes on this graph paper, so 13, 14, I'm up here somewhere roughly. I know this baby's going to follow the asymptotes, so I would be content with your coming down, following it, and then heading out the slanted asymptote. We are not looking for rocket science perfect graphs. We are looking for rough sketches here. So that would do the trick on that one. I know this is getting long, but I feel the need to do just one more example just to make sure you've got it. Let's do a more traditional graph here, just to make sure we've got a clue. This time I think I'll pop my graph square on right now. Okay, this time I want to do the function f of x equals 5x plus 10 over x squared minus 9. Okay, can you tell me right now, is this going to have a horizontal or a slant or slash curvilinear? Big question is the numerator got the higher power? No, it doesn't, so this is going to have a horizontal. Let's, of course, do verticals first. Verticals are where the denominator equals 0. This is really, really, really super duper tough. X squared is going to equal 9, so therefore I have verticals at plus and minus 3. I might as well put them on the graph as well. So at positive 3, I'm going to run an asymptote. At negative 3, I'm going to run an asymptote. Okay, and we already discussed, since the numerator is not higher than the denominator, I'm going to end up with a horizontal. I just need to find it. So if I'm going to find my horizontal, I have to go, what's the highest power? I see x squared. Top doesn't have an x squared, so I'll put a 0x squared. Cancel it, equals 0, so I have a horizontal asymptote at y equals 0. Right smack down the x-axis. This is the way we like them. Like I said, this is a very traditional, typical type of graph you get with rational functions. Okay, the chances are extremely good. On the outer edges, it's going to fall in the corners like a butt crack or a hallway. The center section is usually either a parabola or a scrabola. So we just need to figure out what's happening, and the easiest way to do that to some extent is to find the x and y intercepts. So how do I find the x and y intercepts? Yep, I sub my zeros in. And so if I'm doing x-intercepts, I want to put y equals 0. So that one will actually require a little bit of work. I'm going to come down here toward the bottom. I'm asking myself where this thing will equal 0. Do I need to write the denominator? No, because when I multiply it to the other side, it's going to equal 0. So once again, you don't need to worry about denominators when you're solving for the x-intercepts. If I solve what's left of this, 5x equals negative 10, so x equals negative 2. So I would have an x-intercept at negative 2, 0. And once again, yes, you can cross an asymptote. The horizontal asymptote can be crossed. They're only for what happens as you extend toward infinity. So yep, this baby's crossing at negative 2, 0. All right, my y-intercept is where the x-coordinate is 0, and that, if I sub in there, is going to give me negative 10 over 9. Okay, typically, they're not going to be great numbers, so that's negative 1 and another ninth, so it's just a smidge below here. Okay, that right there, do you think it's going to be a parabola or a scrabola? Well, I'm thinking that does, like, it could be a parabola going upward, could be a scrabola coming downward. We need another point. And in this case, I would be really tempted to, since I plotted negative 2, I'd probably plot positive 2 just to see what's happening. So you just have to try a few more points. If I put 2 in this function, 10 plus 10 would be 20 on top. 2 on the bottom, 4 minus 9 would be negative 5. That would give me negative 4 on that one. So that would tell me that I need to plot the point 2, negative 4, and I think that just answered our question. 1, 2, 3, 4. I'm down here somewhere. Well, that's not looking very parabola-like. I would say this is some form of a scrabola, so yeah, we would guesstimate it's doing something like that. Not exact, but ballparkish. Now, there has to be something, however, out on the outer edges of those asymptotes, so you need to pick a number outside the verticals. If the verticals were at 3 and negative 3, pick another number past 3 and negative 3. Once again, I don't like to do big numbers, so I'm probably going to do 4. If I do 4 here, that'd be 20 plus 10 is 30. 4 on the bottom, 16 minus 9 is 7. 30/7 is about 4 2/7. So at positive 4, I would be 4 2/7 up. All that tells me then is, hey, I must be up here in this quadrant and following my little corner curve up this way somewhere. I need a negative coordinate, and I just kind of ran myself out of space. Going to make myself a little room here. And so I would go ahead and plot, say, negative 4. And if I stick negative 4 in this function, negative 4 on top, negative 20 plus 10 would be negative 10. Negative 4 here would be 16 minus 9, or 7. And so I have negative 10/7, or a negative 1 3/7 roughly. So if I'm over 4, 1, 2, 3, 4, I'm down 1 3/7. That tells me I'm in this lower quadrant here, and I can then see that I need to follow my asymptotes and curve out in that general direction. Once again, these aren't perfect rocket science exact graphs, but they're ballparkish. We get the general shape. So there you go. That's the excitement of rational functions. Most of your problems, please, once again, read the instructions on the actual assignment sheet. Do my instructions. You do not do what the instructions in the book say. Good luck.